Hello, in this lecture we'll find out the area of trapezoid ABCD. In the drawing we have a circle that is inscribed by this trapezoid ABCD. In addition, you know that side AB of the trapezoid is equals to x, side DC equals to 7 over x. This is angle BAD, that is a right angle, and this is angle ATC, that is also equals to 90 degrees in its size. Again, our mission is to find out the area of this trapezoid ABCD. So, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. Here we have quadrilateral ABCD, and we know that in this quadrilateral ABCD, side DC is parallel to side AB, and therefore this quadrilateral is defined as a trapezoid. And again, a trapezoid is a quadrilateral with one pair of parallel sides. So what is the area of this trapezoid ABCD? The two parallel sides are defined as the bases of this trapezoid ABCD. That is to say, side DC is the base of trapezoid ABCD, and side AB is also the base of trapezoid ABCD. And we know that DC equals to A, AB equals to B. So the area of this trapezoid ABCD is equals to the sum of its bases, that is to say DC plus AB. DC is A, AB is B, and therefore it is A plus B times the I to the base, that is H, over 2. Again, the area of this trapezoid ABCD equals to the sum of its bases, that is A plus B, times the height, that is H, over 2. Here the height H must create 90 degrees with its two bases. So here we have 90 degrees, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Again, the area of this trapezoid ABCD equals to A plus B times H over 2. Okay? So, here, first of all, we will define the points of tangency of this trapezoid with the circle with letters. That is to say, we will define the point of tangency of side AB or tangent AB with this circle, this point as E. Likewise, we will define the point of tangency of side AD or tangent AD with this circle, this point as F. We define the point of tendency of tangent DC or side DC with this circle, this point as G. And finally, we define the point of tendency of tangent BC or side BC with this circle as H. So here we can implement rule 2. We'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have this circle, and we have this is common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. So whenever we have a circle and the common external point, and from the common external point you draw two tangents to the circle, then the lengths of those two tangents must be equal to each other. In this case, PA equals to PB. You can actually implement rule 2 in our drawing, because in our drawing we have the common standpoint point A. From the common standpoint point A, we have two tangents to this circle, tangent AE and tangent AF. And according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of AE as y, then the length of AF must be also equal to y, because of the fact that AE is equal to AF according to rule 2. Likewise, we'll focus on this common external point B. From this common external point B, we have two tangents to this circle, tangent BE and tangent BH. And according to rule 2, they are equal to each other. That is to say, BE is equal to BH. So if we define the length of tangent BE as Z, then BH must be also equal to Z, because of the fact that according to rule 2, BE equals to BH. Likewise, we'll focus on this common external point C. From this common external point C, we have two tangents to this circle, tangent CH and tangent CG. And according to rule 2, they are equal to each other. That is to say, CH equals to CG. So if we define the length of tangent CH as M, then the length of tangent CG must be also equal to M according to rule 2, because of the fact that HC equals to CG. And finally, if we focus on this common external point D, from this common external point D, we have two tangents to this circle, tangent DG and tangent DF. And according to rule 2, they are equal to each other. That is to say, DG equals to DF. So if we define the length of tangent DG as T, then the length of tangent TF must be also equal to T according to rule 2. Okay, so in the next step we will add side AB to the opposite side DC. Again, we will add side AB to the opposite side DC in this trapezoid ABCD. So it is AB plus DC. AB plus DC. So what is the value of AB? AB equals to Y plus Z. This is again AB equals to Y plus Z plus DC. What is the length of DC? From now it is very easy to see that DC equals to T plus M. Again, DC equals to T plus M. DC equals to T plus M. Okay. Likewise, we will join side AD to the opposite side BC. AD plus BC. AD plus BC. So what is the value of AD plus BC? From the drawing it is very easy to see that AD equals to Y plus T. Again, AD equals to Y plus T. Read again here, AD equals to Y plus T plus BC. What is the value of BC? BC equals to Z plus M. Again, BC equals to Z plus M. BC equals to Z plus M. So here can arrange the we can change the order of the letters here, and we get that Y plus Z plus t plus m, it is equals to y plus t plus z plus m. Okay, according to the rule that a plus b equals to b plus a. Therefore, we can change the order of the letters. Instead of y plus z plus t plus m, we can write down y plus t plus z plus m. So in conclusion, we actually found out that ab equals to y plus t plus z plus m, and AB plus DC equals to y plus t plus z plus m, and AD plus BC also equals to y plus t plus z plus m. Therefore, those two expressions are both equal to the same expression, and therefore they must be equal to each other. Okay, so we can derive from those two equations that AB plus DC equals to AD plus BC. Okay, so this is equation 1. In the next step, we'll define side BC as B. So BC equals to B according to our definition. And we'll define side AD as A. Again, AD, side AD of the trapezoid is equals to A according to our definition. Okay, and according to equation 1, we found out that AB plus DC equals to AB, again, AB plus DC equals to AD plus BC. Repeat again. We already found out that according to equation 1, AB plus DC equals to AD plus BC. Okay, so here AB equals to x according to what is given as the question. So we substitute AB by x plus DC. DC equals to 7 over x according to what is given as the question. Here DC equals to 7 over x. So we substitute DC in equation 1. Here we substitute DC in equation 1 by 7 over x. And it is equals to AD plus BC. AD equals to A according to our definition plus BC. BC equals to B according to our definition. So in total, we actually found out that according to equation 1, x plus 7 over x equals to a plus b. Again, according to equation 1, we actually found out that x plus 7 over x equals to a plus b. Okay, so in the next step, we'll do a construction. That is to say, from point B, we'll draw perpendicular on DC. Again, from point B, we'll draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also is also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and side DC as point S. Actually, by doing this construction, we created the quadrilateral ABDS. This is quadrilateral ABSD or ABDS. Inside this quadrilateral ABDS, we have 1, 2, 3 right angles. The sum of three right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Okay. So inside quadrilateral A, B, D, S, we have four right angles, and we know that any quadrilateral that has four right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral A, B, D, S that has four right angles as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABDS, side AB must be equal to the opposite side DS. Again, side AB must be equal to the opposite side DS in rectangle ABDS. But side AB equals to X according to what is given as the question, and therefore side DS, this is side DS, that is also must be equal to X. Likewise, according to the same rule, in the same rectangle ABDS, side AD must be equal to the opposite side BS. But side AD equals to A according to our definition, therefore side BS must be also equal to A. By doing this construction, we actually created here the right green triangle, BMC. This is the right green triangle, BMC. We have already found out that side BS of this right triangle BSC is equal to A. The hypotenuse BC equals to B according to our definition. And finally, what is the length of this side SC of the right green triangle, BSC? For the drawing, it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. So write it down. SC is equals to DC minus DS. So SC equals to DC. DC is 7 over X according to what is given as the question, minus DS. DS equals to X. So in total, SC equals to 7 over X minus X. So write it down. Here, SC in total equals to 7 over X minus X. So in the next step, I'll copy the right green triangle BSC in a new page, and we will implement the Pythagoras theorem on this right green triangle BSC. Okay. Here by PT is the abbreviation for Pythagoras theorem. Side BS equals to A. The hypotenuse BC equals to B. And finally, we just write down for now that side AC equals to 7 over X minus X. So actually, this is the right green triangle BSC that I copied from the original drawing. here by PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle BSC, the hypotenuse is BC, and therefore the square of the hypotenuse will be equal to BC square. And BC square equals to BS square plus SC square. Okay. This is equation 2. So BC is B, therefore BC square is B square. And it is equals to BS square. BS is A, therefore BS square is A square plus SC square. SC is 7 over X minus X, therefore SC square is 7 over X minus X square. So here we use the following trigonometric identity that states that A minus B square is equals to A plus B square minus 4 times A times B. Repeat again, A minus B square equals to A plus B square minus 4 times AB. If you open the brackets here, you will definitely see that those two sides are equal to each other. Okay, so according to equation 2, we actually found out that B square equals to A square, and we have plus 7 over X minus X square. This is equation 2, we have here plus 7 over X minus X square. And according to this trigonometric, this algebraic identity, that A minus B square equals to A plus B square minus 4 times AB, we will get that 7 over X minus X square will be equal to 7 over X plus X square minus 4 times 7 over X times X. Okay? If you just substitute A by 7 over X and B by X, you will get that 7 over X minus X square, according to this algebraic identity, equals to 7 over X plus X square minus 4 times 7 over X times X. Here we have X in the numerator and X in the denominator, so X will get cancelled. So according to equation 2, we actually found out that B square equals to A square plus 7 over X plus X square. Here we have 4 minus 4 times 7 is minus 28. So here we will add 28 to this equation 2. And you get that according to this equation 2, B square plus 28 equals to A square plus 7 over X plus X square. This is according to equation 2. While according to equation 1, we have already found out that 7 over X plus X equals to A plus B. And again, according to equation 1, we already found out that 7 over X plus X equals to A plus B. Therefore, we can substitute 7 over X plus X in this equation 2 by A plus B. We'll do it now, and we get that according to equation 2, we have here 7 over X plus X equals to A plus B. So here, according to equation 2, we have here B square plus 28 equals to A square plus 7 over X plus X square. And 7 over X plus X equals to A plus B according to this equation 1. So we substitute 7 over X plus X by A plus B. And we have to square it, because we have here square. So actually in conclusion, according to equation 2, we found out that b squared plus 28 equals to a squared plus a plus b squared. So here we'll open the brackets on this side of the equation 2 and get that according to this equation 2, b squared plus 28 equals to a squared, and a plus b squared, according to the algebraic identity that a plus b squared equals to a squared plus b squared plus 2 times ab will be equal to a squared plus b squared plus 2 times a times b. So actually according to equation 2, we found out that b squared plus 28 equals to a squared plus a squared plus b squared plus 2 times ab. Here we have b squared on both sides of the equation 2, so b squared will get cancelled. After we cancel b squared, in this side of the equation we left only with 28, that is equals to a squared plus a squared is 2a squared plus 2ab. So according to equation 2, we actually found out that 28 equals to 2a squared plus 2ab. So here we divide this equation 2 by 2. And finally we get that according to this equation 2, 2a squared over 2 is a squared plus 2ab over 2 is ab, and 28 over 2 is 14. So in conclusion, we actually found out that according to equation 2, a squared plus ab equals to 14. This is according to equation 2, while according to equation 1, we have already found out that 7 over x plus 7 over x equals to a plus b. So this is the two equations that we have here. So in the next step, we'll find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, we have already found out that the area of this trapezoid ABCD equals to a plus b, that is the sum of the parallel bases, times h, that is the height, over 2. Again, the area of this trapezoid ABCD equals to the sum of the bases, that is a plus b, times the height, that is h, over 2. So use this formula in order to find out the area of this trapezoid ABCD. We know that the two bases of this trapezoid ABCD are AB and DC. Why? Because we know that AB is parallel to this DS, because of the fact that we know that in any rectangle the opposite sides are parallel to each other. Therefore, DS is parallel to AB, but DS is part of the straight line DC and is parallel to AB. So if part of a straight line is parallel to another straight line, then the straight line DC itself must be also parallel to AB. Therefore, the two bases of trapezoid ABCD are DC and AB because of the fact that DC is parallel to AB. So the area of trapezoid ABCD will be equal to AB plus DC, that is the sum of its two bases. The two bases are parallel to each other. AB plus DC times the height. The height must be perpendicular, must create 90 degrees with the two bases. You can see here that AD creates 90 degrees with the two bases. Therefore AD is the height. So it is times AD over 2. Repeat again, the area of trapezoid ABCD equals to the sum of its two bases that are parallel to each other. That is to say, it is AB plus DC times the height, that is AD over 2. So AB is x according to what is given us in the question, plus DC. DC is 7 over x according to what is given us in the question. Times AD. AD equals to A according to our definition. A over 2. So actually found out that the area of trapezoid ABCD is equal to x plus 7 over x times A over 2. But according to equation 1, according to this equation 1, we know that x plus 7 over x equals to A plus B. So we can substitute x plus 7 over x in this formula by A plus B. We'll do it now. So instead of x plus 7 over x, we'll write down A plus B according to equation 1 times A over 2. So here we'll open the brackets of this expression, and we get that the area of triangle of trapezoid ABCD equals to A times A is A squared plus AB over 2. So here we have A squared plus AB, but we already found out that according to equation 2, A squared plus AB equals to 14, therefore we can substitute A squared plus AB here by 14. We'll do it now, and get that A squared plus AB is 14, and 14 over 2 is 7. So we found out that the area of trapezoid ABCD is equal to 7 square units. Repeat again, the area of this trapezoid ABCD is equal to 7 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this trapezoid ABCD. In the drawing, we have this circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of this trapezoid ABCD is equal to x. Side DC, the opposite side DC is equal to 7 over x. This is angle DAB, that is right angle, and this is angle CDA, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. Okay, so first of all, what is a trapezoid? Trapezoid is a quadrilateral with one pair of parallel sides. Again, trapezoid is a quadrilateral with one pair of parallel sides. So we have here quadrilateral ABCD, and in this quadrilateral ABCD we know that side DC is parallel to the opposite side AB, and therefore this quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. That is to say, side DC is parallel to the opposite side AB, and therefore this quadrilateral ABCD is a trapezoid. And the two parallel sides are defined as the bases. So DC is the base and AB is also the base. DC equals to A, AB equals to B, and therefore the area of this trapezoid ABCD will be equal to the sum of its two bases, that is to say A plus B, times the height, that is edge, over 2. Again, the area of this trapezoid ABCD equals to the sum of its two bases that are A plus B times the height that is h over 2. The height must create 90 degrees with the two bases. Here, the height h creates 90 degrees with the base AB, and the height h also creates 90 degrees with the other base DC. This again equals to 90 degrees. Okay, again the height, the area of this trapezoid ABCD equals to A plus B times h over 2. Okay, so first of all, actually gave we defined the points of tangency of trapezoid ABCD with this circle with letters. We defined the point of tendency of side AB of tangent AB with this circle, this point as C. Likewise, we defined the point of tendency of side BC of tangent BC with this circle here, this point as H. We defined the point of tendency of tangent AD of side AD with this circle, this point as F. And finally, we defined the point of tendency of tangent DC with this circle as G. So here we can implement rule 2. I'll repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle, and we have, this is the common external point, point P. From this common external point, point P, we have two tangents to this circle. We have tangent PA that is tangent to this circle here at this point A, and we have tangent PB that is tangent to this circle here at point B. According to this rule 2, whenever you draw two tangents from a common external point to a circle, the lengths of those two tangents must be equal to each other. In this case, PA must be equal to PB. So actually we can implement rule 2 in our drawing. One, because in our drawing, we have here the common external point, point A. From this common external point, point A is the common external point in relation to this circle, of course. Because it is not located inside the circle, nor on the circle. It is located outside the circle, therefore it is defined as a common external point, point A, in relation to this circle. From this common external point, point A, we have two tangents to this circle. We have tangent AE and tangent AF, and according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of tangent AE as y, then the length of tangent AF must be also equal to y according to rule 2. Okay, likewise, if we focus on this common external point, point B, from this common external point, point B, we have two tangents to this circle, tangent BE and tangent BH. And according to rule 2, they are equal to each other. That is to say, BE equals to BH. So if we define the length of tangent BE as Z, then the length of tangent BH must be also equal to Z according to rule 2. Likewise, if we focus on this common external point, point C, from this common external point, point C, we have two tangents to this circle. We have tangent CH and tangent CG. And according to rule 2, they are equal to each other. That is to say, the length, if we define the length of tangent CH as M, that is to say CH equals to CG, of course. And if we define the length of CH as M, then the length of CG must be also equal to M because of the fact that CH equals to CG. And finally, if we focus on this common external point, point D, from this common external point, point D, we have two tangents to this circle. We have tangent DG and tangent DF. And according to rule 2, they are equal to each other. That is to say, DG equals to DF. So if we define the length of tangent DF as T, then the length of tangent DG must be also equal to T, according to rule 2. So here we added side AB to the opposite side DC in this trapezoid ABCD. So it is AB plus DC. So what is the value of AB plus DC? AB equals to Y plus Z. DC equals to T plus M. So in total, AB plus DC equals to Y plus Z plus T plus M. Okay, AB plus DC equals to Y plus Z plus T plus M. Actually, if we change the orders of these letters, we can definitely change the orders of the letters according to the algebraic identity that A plus B equals to B plus A. So Y plus Z plus T plus M equals to Y plus T plus Z plus M. We just change the orders of these letters. And here, likewise, we added side AD to the opposite side, side BC, in this trapezoid ABCD. So what is AD plus BC? Again, what is the value of AD plus BC? AD equals to Y plus T. BC equals to Z plus M. So in total, AD plus BC equals to Y plus T plus Z plus M. So AD plus BC equals to Y plus T plus Z plus M. So actually found out that AD plus DC equals to Y plus T plus Z plus M, and AD plus BC also equals to Y plus T plus Z plus M. And therefore, those two expressions are equal to the third expression, and therefore to the same third expression, and therefore they must be equal to each other. That is to say, AB plus DC, this expression must be equal to this expression, that is AD plus BC. So, in conclusion, we found out that AB plus DC equals to AD plus BC. So, what is AB plus BC, or AB plus DC? AB is X according to what is given as the equation. DC is 7 over X. So, in total, AB is X, DC is 7 over X, and it is equal to AD plus BC. We actually define side AD as A, and we define side BC of this trapezoid ABCD as B. So AD is A, and BC is B, and therefore AD plus BC equals to A plus B. Again, AD plus BC equals to A plus B. So in total, according to equation 1, we actually found out that X plus 7 over X equals to A plus B. In the next step, we did a construction, that is to say, from point B, we draw perpendicular on DC. Again, from point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B inside DC as point S. By doing this construction, we created here quadrangle ABSD. This is quadrangle ABSD. Inside this quadrangle ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside this quadrangle ABSD, we have 4 right angles, and we know that any quadrangle that has 4 right angles must be this rectangle, if not a square. So we relate to this quadrangle ABSD as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB equals to the opposite side DS. But AB is X, therefore DS must be also equal to X. Likewise, according to the sum rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD according to our definition is A, therefore BC must be AD is A, therefore side BC must be also equal to A. Okay. Actually, by doing this construction, we created the green right triangle, triangle BCS. This is right triangle because of the fact that this angle equals to 90 degrees. So, in this green right triangle BSC, side BS equals to A. The hypotenuse BC equals to B. So what is the length of side SC of the green right triangle. From the drawing, it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. And again, SC equals to DC minus DS. DC is 7 over X, and DS is X. So in total, SC is 7 over X minus X. Again, SC is 7 over X minus X. In the next step, I copy this right green triangle BSC in an equation. We implemented the Pythagoras theorem on this right triangle BSC. So actually, this is the right green triangle BSC that I copied from the original drawing. We already found out that BS equals to A. We just found out that SC equals to 7 over X minus X, and the hypotenuse BC equals to B. According here by PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle BSC, the hypotenuse is BC, therefore the square of the hypotenuse is BC square, and it must be equal to BS square plus SC square. So BC is B, therefore BC square is B square, and it is equals to BS square. BS is A, therefore BS square is A square, plus SC square. SC is 7 over X minus X, therefore SC square is 7 over X minus X square. So in conclusion, according to equation 2, we found out that B square equals to A square plus 7 over X minus X square. Here we have the algebraic identity that A minus B square equals to A plus B square minus 4 times AB. If you just open the brackets in both sides of the equation, you will definitely see that those two sides are equal to each other. So we use this algebraic identity, and according to equation 2, we have here B square that is equal to A square, and X, 7 over X minus X square, according to this algebraic identity, will be equal to 7 over X plus X square minus 4 times 7 over X times X. Okay, here we have X in the denominator and X in the denominator, so X will get cancelled. Actually, according to equation 2, we found out that B square equals to A square plus 7 over X plus X square, and here we have 4 times minus 4 times 7 is minus 48. So here we added 28 to this equation, equation 2, and actually found out that according to equation 2, B square plus 28 equals to A square plus 7 over X square. This is according to equation 2, but according to equation 1, we have already found out that 7 over X plus X equals to A plus B, therefore we can substitute 7 over X plus X in this equation 2 by A plus B. We did it, and we shall found out that according to this equation 2, B square plus 28 equals to A square plus A plus B. And again, we shall found out after we substituted 7 over X plus X by A plus B, we found out actually that according to equation 2, B square plus 28 equals to A square plus A plus B square. Okay, so here we open the brackets, this side of the equation 2, we found out that according to equation 2, B square plus 28 equals to A square, and A plus B square equals to A square plus B square plus 2 times AB. Here we have B square on both sides of the equation, so B square will get cancelled. After cancelled B square, in this side of the equation 2, we left only with 28. On the other side of the equation 2, we have A square plus A square is 2A square. And we have 2A square plus 2AB. So conclusion, according to equation 2, we actually found out that 28 equals to 2A square plus 2AB. We divided this equation 2 by 2, and finally found out that 28 over 2 is 14, 2A square over 2 is A square, and 2AB over 2 is AB. So in total, actually, according to equation 2, we found out that A square plus AB equals to 14. This is according to equation 2, while according to equation 1, we have only found out that X plus 7 over X equals to A plus B. So what is the area of trapezoid ABCD? The area of trapezoid ABCD is equals to the sum of its two bases. The two bases are AB and DC. Why? Because we know that AB is parallel to DC. Why AB is parallel to DC? Because we know that ABSD is a rectangle, and we know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to side DC. Side AB is parallel to side DS. But DS is part of the straight line DC and is parallel to AB, therefore the straight line DC itself must be also parallel to AB. So we know that DC is parallel to AB, therefore trapezoid ABCD, the two bases are AB and DC because they are parallel to each other. So the sum of the two bases is equal to AB plus DC times the height. The height is AD because AD creates 90 degrees with the two bases. This angle equals to 90 degrees and this angle equals to 90 degrees. So the height is AD divided by 2. Again, the area of triangle and area of trapezoid ABCD equals to the sum of its bases, that is AB plus DC, times the height, that is AD over 2. And again, the area of triangle trapezoid ABCD equals to the sum of the two bases, that are AB plus DC, times the height, that is AD over 2. AB is x according to what is given as the question. DC is 7 over x according to what is given as the question. AD, side AD equals to A according to our definition. AD equals to A. So in conclusion, actually found out that the area of triangle of trapezoid ABCD equals to x plus 7 over x times A over 2. But according to question 1, we have already found out that x plus 7 over x equals to A plus B. Therefore, we can substitute here x plus 7 over x by A plus B. We did it. We found out that x plus 7 over x is A plus B times A over 2. Here we opened the brackets and found out that here we have A squared plus AB over 2. But according to equation 2, we already found out that A squared plus AB is 14. So we can substitute A squared plus AB here by 14. We did it and found out actually that the area of trapezoid ABCD equals to 14 over 2, that is 7. So in conclusion, actually found out that the area of trapezoid ABCD equals to 7 square units. I repeat again, the area of this trapezoid ABCD is equals to 7 square units. Okay, thank you very much.